I, for one, am extremely grateful for the opportunity that Perkins has provided me with. And Perkins can provide that opportunity because of the kind of support that it receives from the community. It is vitally important. And at the end of my talk, I'll explain to you why I've got this tie on. And it's to do with the support that I've received from the Perkins. So, I'm one lab at the Perkins. There are many labs. Your support has enabled me to achieve incredible outcomes. And I'll talk to you about what I considered my bucket list of experiments I put in a category that were not possible to do. This was at about the time, well now, 12 years ago when I was supposed to retire. I'm 77. And at that stage I thought, well, these I have to put aside because they're not possible. But by virtue of the resources that have been provided to me through the support of people who fundraise for the Perkins and for the work of people like yourselves here over here, it's enabled this work to be done. And I will share some of that with you today. So I work on liver cancer. And what I would like to emphasize, first of all, the dire situation that exists with liver cancer. And here, there are 2 points that I wish to emphasize. First, look at cancers all time. The beauty of this is the graph, the slope is coming down. It means that we are saving many more lives. While cancer incidence is increasing because we're living longer, we are still able to achieve this outcome. So that decrease, this figure here is called mortality to incidence ratio. How many people die as a result? How many people that we detect have the cancer and what percentage of them die? All right? So a mortality incidence ratio here of 0.3 means that we are saving 70% of the people who we detect cancer in. In contrast, this is the picture for liver. One, look at the slope of the line. It's much, much shallower. Second, the mortality to incidence ratio, the MIR here, is 0.9. It means that we have 9 out of 10 people who are detected with liver cancer die. Okay. Here, 3 out of every 10. So that's a huge difference. Why is this so? Well, it is the 7th most common cause of cancer deaths in Australia. We had 2,200 people pass away as a result of getting liver cancer, and its incidence is increasing due to lifestyle practices. We're consuming too much alcohol, we are consuming too many calories, and there is increased drug use in our community, and sharing of needles passes the hepatitis virus across our community. Hence, this mortality incidence ratio is the highest of all cancers. And it's that the reason is because we detect liver cancers and liver disease by elastography very, very late. The cancer is well advanced, and we all know early detection is a mitigating factor and allows us to treat people the earlier we can detect the cancer. Blood tests are uninformative. And briefly, I need to address this because the blood test that we have actually manages the death of liver cells. But if the liver is not functioning properly, our liver tests aren't very informative. Okay, so that's the bottom line. I could go into that more if there are questions. By the way, please at the end ask questions. And I love to engage, and I think one of the opportunities here is to inform the community about what we're doing, but also to tell you what we can do about these terrible diseases that affect us. And the treatment options are limited. There are about 2 to 3 FDA-approved drugs to treat advanced liver cancer. And sorafenib extends the lifespan of a liver cancer patient by 5 months. 5 months. To me, that's a very, very poor outcome. And worse still, when you talk to clinicians, sorafenib has dire side effects. Okay, so there we go. So what are we doing about it? Well, you know, I really am a dinosaur in this place because I've been around for such a long time. But I spent 40 to 50 years of my life working on liver. We develop our achievements, we develop a mouse model where the mouse consumes too many calories, gets fatty liver disease, and this induces a liver progenitor stem cell in their liver, and then after we find these, we get the hepatocellular carcinoma, which I've called here HCC. So these stem cells, I've claimed, are a precursor to the cancer. One of my bucket list experiments is to show that the stem cell is the source of the liver cancer. All right? I'm not saying this happens all the time, but I believe that they are a potential origin of the liver cancer. And we have identified these progenitor cells in alcoholic liver disease, in hepatitis C, in genetic hemochromatosis. That's also a condition through no fault of their own. Some people have a genetic disorder where they absorb too much iron and it toxifies the liver and causes liver damage and also causes liver cancer. NAFL is short for non-alcoholic fatty liver disease. And I've got here the canary. I believe that these liver progenitor stem cells, to have an analogy, coal miners in the past used to bring a canary down into the coal mine. And when that canary falls over and dies, then they get out of the mine. It tells them, it's a sentinel. And I believe that my liver progenitor stem cells are a sentinel. And they could be the way we detect impending liver cancer and liver disease. So that is what we are currently working on. Now, the liver progenitor cells are not all bad. They're good because they are there to regenerate and repair the liver. But, as many of you will know, our liver actually regenerates very, very well. If you lose some of your liver, let's say in a car accident, in about 6 months you'll restore most of what you've lost. And the liver is such an important organ that you will recover weight-wise exactly what you lost. Its growth is regulated so precisely. I keep telling all the people who work around me how important the liver is because L-I-V-E is live. Without your liver, you're a goner. Okay, so what we have also shown is that we've demonstrated the importance of inflammation in regulating this liver progenitor cell proliferation and differentiation. But we also believe there's a dark side to these cells. If they are asked to work for too long and too vigorously, they'll turn to the dark side and present you with liver cancer. So that is the hypothesis. But the good ones of these cells, we've established mouse and now human liver progenitor cells that we can do research on. The questions that we are asking is, what makes them become cancer cells? Right? What makes them go to the dark side? But we can use these cells and make liver organoids. We can use them to study what these cells do. And we have actually shown in a test tube that we can grow these cells up and they become bile duct cells and hepatocytes, liver cells. 2 different types of liver cells. So they are at least bipotential. And this is why I call them a progenitor cell and not so much a stem cell. Okay, because a stem cell has usually more options. And looking at these cells in detail, we can understand how liver cancer develops. We have also got a bit of activity that we're doing, which is drug screening. Because while I've been growing these cells, some of them become rogue. So we've got the good guys and the bad guys, the good apples and the rotten apples. And one thing that I think we need to address is when we're looking for drugs to treat liver cancer, we need to find a drug that is selective, that it affects the rogue cells and leaves the normal ones alone. There are a plethora of drugs. People isolate all sorts of stuff that they come to me and say, George, will you test them on your cancer cells? I say, yes,
But more importantly, we need to test it on the cancer cells, the bad guys, but make sure they don't hurt the good guys. And that is how we are currently taking drug screening. I'll share some of that information with you. Okay, so here we go. We actually are blessed, and our collaborators have been very, very supportive. Someone over in Melbourne discovered a way to mark these cells using an antibody. So we can actually, all the brown cells here you see are the progenitor stem cells. In alcoholic liver disease, a liver biopsy shows in a chronic alcoholic consuming lots of alcohol, these cells are there. In fatty liver disease, not so many, but they are there nevertheless. Somebody with hepatitis C, many, many cells. So the brown cells are the liver progenitor stem cells, okay? And we can identify them. So if we can take hold of the liver biopsy, we can look to see whether these cells are there. And for me, when they are there, that's not good news because the liver now is using these cells to repair itself rather than pre-existing hepatocytes, okay? So it's using plan B, and when it's using plan B, it signals something's wrong with this patient. So coming back to my analogy with the canary, so we have identified and we've counted these cells and we've published a paper. We were the first people in the world to publish in the American Journal of Pathology that these cells are present in people with liver disease. And all of these people statistically have a higher incidence of liver cancer. So what we're trying to do is draw a line between the liver's stem cell that's gone rogue and the liver cancer. So we propose that the liver stem cells actually predict the severity of liver disease and they can predict liver cancer development. That's what we propose. That's our hypothesis. That's a working hypothesis in our lab. But importantly, my mate in Melbourne tells me that there's some evidence that this antibody they've made reacts to a protein on the surface of these liver stem cells, and it might be shed. If the cells shed it, it may go into the blood. And therefore, the antibody might be able to detect what is shed by the stem cells in the blood. And this opens up the possibility of developing a liver blood test. To continue my analogy, maybe the canary in the coal mine is shedding a few feathers, and we look for the feathers. Okay? So we're looking for the feathers in the blood. So I told you about my bucket list projects, and here they are. There are 5 of them here. And for a long time, I was in fact criticized at meetings in America and Europe. When I stood up and talked about liver stem cells, they said, "George, you're crazy. The liver actually grows so well when it's damaged. Why the hell does it need a stem cell?" Right? And the reviewers on my grants who have said, "Sorry, George, no money." Even if a liver stem cell exists, what is it doing? It may exist, but it has no functional significance. Right? So many rejections I've had for grant funding has taken this attitude. There's also another attitude that exists out there. If you go to funding organizations to support liver research, especially what I'm doing, alcoholics, people who consume too many calories, who are obese, intravenous drug users, they bring it upon themselves. Right? They do not have the sympathy of the people out there who are giving money for research. So that is another problem. And this is why your support to the Perkins and Perkins' support to me is so valuable. Okay, so here is my bucket list. I want to identify this liver stem cell in mice with fatty liver disease, the model that I developed. And I want to prove that beyond a shadow of a doubt, and for want of a better term, stick it to the criticizers. I want to establish a human liver stem cell line that we can use to develop drugs. And I want to develop a drug that selectively targets liver cancer cells, not healthy liver cells, so that we have something selective and we don't put the people with liver cancer through hell with a treatment that has got terrible side effects. I want to develop a blood test that informs clinicians of the state of liver disease in patients, especially if they develop liver cancer eventually. Then they can mitigate. We can give them a reason to change their lifestyle. We can give them a reason to look after their liver. And I want to understand what changes a normal liver stem cell into a raw liver cancer stem cell. What are the molecular, the mutational changes? Why does it take on this dark side? Now, some of the things that I want to do have been enabled. My bucket list, I'm actually now working on some of those things because there are facilities available here. 5 years ago, I never dreamed that this device could exist. What I'm showing you here is a machine that will look at the activity of thousands of single cells from a piece of liver. So again, I'll give you an analogy. If you were to go and get your boost juice made up from various fruit, and you had 10 fruit, and you mashed it all up, and you gave the person a drink, can you tell me what are the components of this drink? Well, if you put it into this machine, the machine will tell there's watermelon, there's kiwi fruit, there's etc., etc. Okay? It can actually identify the individual components. And this machine makes little beads enclosed in a picoliter bubble. A picoliter is a trillionth of a liter, right? And it's so small that it will only allow it to enclose one cell. And you make this bubble with all the reagents inside that cell. So let's look at that pink cell. It's got all the reagents in there, and then you carry out, that now becomes your test tube. You are only looking at the activity and the behavior of one cell. You can then now genetically and transcriptomically and proteomically identify all the properties of that single cell. And it does 10,000 cells in one go. To crank this machine out, for one of my experiments, is $5,000. It's a lot of money. But that machine is about $1 million. Okay? And I have the privilege of accessing this right here. Okay? So, we can actually tell a single cell's activity, its pattern of activity, and particular cell types and rare cells can be identified. And we concluded these experiments. A rare cell with the features of a liver stem cell is present in a mouse with fatty liver disease. So one bucket list accomplished. And here's the data. We published this. The livers, so coming back to my analogy, so let's say this watermelon, this kiwi fruit, etc. But look at the small population. That's where my liver stem cells are. So this machine analyzes the 30,000 cells and puts them all up on this map and tells me that here is a fraction of cells that has got the property of liver progenitor cells. There's only 103 of them in that whole panel. But nevertheless, mission accomplished. We can identify this cell. This was published in Cell Genomics just this year. It's not just the fact that I'm here and equipment is here, but I have morning tea, afternoon tea, lunch, with a whole lot of very clever people, all right? And I keep telling them how important the liver is, and we're collaborating on this work. So that's one. The other one I want to accomplish here is the human liver progenitor stem cell line, because I got lots and lots of mouse cell lines, and my reviewer said, very good, mouse, but show me human. Okay, and that's true. That's reasonable criticism. This has been made possible in this place. We now have access to human liver samples. We are actually collecting through the Liver Cancer Consortium, the collaboration, liver biopsies from all across all the hospitals in Perth. What I do with these cells is I actually make them into a dome, and cells migrate out of it, and you can see here. It's taken 3 months, and it will probably take a year, but I'm growing these up, and a colleague of mine here, Tesnuva, is characterizing these cell lines. Right? We're actually growing them individually from one cell, a clone. And we're screening clones and looking for a human liver stem cell. And we're on our way. So this is in progress. Now, off the Indian Ocean, people are collecting sponges. They are unique. They are a special type of sponge that these people are collecting. And I'm in collaboration with the chemists. I think they dredged the Indian Ocean off the West Australian coast and identified 140 separate types of sponges. A research student of mine extracted the chemicals from these sponges, and he was testing them. Out of 140, he found 2, and I'll talk about one of them. One of the extracts, okay, so this is a fairly complicated slide, but I hope I can explain it clearly enough to you. So here's my normal liver stem cell, and here is the cancerous guy, the bad guy. Here is the approved drug affecting the normal cell because it stops it dead in its tracks to grow. And here it is in blue, the approved drug in blue. So it's affecting the cancerous stem cell, but it's also affecting the normal cell. Okay? And that's sorafenib. That's what our patients are getting. In contrast, if we have nothing, no drug in green, my normal liver stem cell grows, and the cancerous stem cell, no drug grows. But if we put the sponge extract in, look at this. The red line is very close to the green line. No effect. But look at the green line and the red line here. The sponge extract is stopping the cancer stem cell in its tracks, and look at the growth in it. Okay, so we are finding one of these sponges actually makes something that is selectively toxic to the cancer cell and leaving the normal ones alone. So that's where we are. So how difficult it is to find the active ingredient. We take this sponge extract, they put it into a liquid chromatograph, and we're getting 1,500 peaks. Which one is the active ingredient? That's what we're after. So a long way to go, but it is in progress. Okay, I've told you about how difficult it is to get funding to develop a blood test. Because the people that we want to test, they've asked for trouble. They deserve it. Okay, so again, another collaborator of mine has recently taken up a position at the Children's Hospital. Marcello Leo is interested. He was in Melbourne developing this antibody that actually looks at the liver stem cell. And they showed that it is actually shed into the blood. And I said to Marcello, Marcello rang me up and said, George, I'm back from Melbourne, let's collaborate. I said, what on? And he said, well, do you know that the children with cystic fibrosis that I encounter, some of them have a liver condition. But we cannot predict which ones are going to have it, and we only detect it very, very late. I said, well, can you get hold of biopsy samples? Can you get hold of blood? I'll look at the biopsy and see whether my stem cells are there, and we'll look in the blood to see whether they shed the feathers into the blood. And so we embarked on this project. And what you see here is the preliminary evidence that we sent to the Cystic Fibrosis organization, Cystic Fibrosis Australia, and they've actually provided some seed funding to see this project through. Okay, so what we have here, these 4 red dots here are cystic fibrotic kids that have got a liver disease. And the feathers are there. Okay? So this means that we potentially may have a blood test that tells us that these kids have got a liver condition. That square dot up there is actually a fatty liver disease patient who has developed liver cancer. So I put that in. That's what you may call that moonlighting, but I'm doing some work on adults as well. But what is important, I think I need to show you the full data, and this guy here, this child here, has got a very high level of this protein, but it turns out that our assay is not perfect. We found that this blood sample actually had a lot of hemolysis. A lot of red cells have been broken up, and it's bright pink, the blood. And that blood sample then gives us a false positive. And we have to do more work to eliminate that. Nevertheless, the children that are normal are down here, and the children that have got liver disease are up here. Interesting information, but I now have to look for this pattern in at least 100 samples, not 10. By the way, these samples were sent to me from Queensland, blind. I didn't know which was the ones that had the disease. We picked 4 out of the 4 patients that had a liver condition. So this is also a work in progress. And just yesterday, 2 days ago, we put an application in to Telethon Kids for funding. So if it's kids and it's cystic fibrosis, I think we have sympathy. And finally, what we want to understand is what makes a liver stem cell cancerous. I put up this picture here to show you that the progenitor cells becomes a normal liver, or it becomes a normal cholangiocyte, or it becomes a liver cancer. What makes it take this path? And interestingly, again, working here, I work alongside some bioengineers. And I put this picture up to show you that here is a fibrotic area where the brown cells, the stem cells, are abundant, and here are some good hepatocytes, slightly positive, next to them. This is a very stiff area. Young's modulus, which is a measure of stiffness, greater than 20 kilopascals. And in the body of the liver is about 4, which is very soft. The engineers now have devised a way for me to take my cells and put them into stiff gels or soft gels. And lo and behold, in soft gels, the cells become liver cells. In stiff gels, they become cholangiocytes, a bile duct. Question, do they take on the properties of the cancer cell? This is what we're currently investigating. So that's a work in progress. So to understand what makes the liver stem cell cancerous, we are now able to take them and put them into put the engineers in, where we put them in an environment that's soft or stiff, and we discovered that the stem cells behave very differently. They are more like cancer cells and less able to produce healthy cells and repair the liver if they are in a stiff environment. We have some preliminary evidence, and we're still digging.